This video is for those of you who are preparing for the second exam of your first semester for organic chemistry. In the full-length extended version of this video, we're going to cover 4 key topics: stereochemistry, SN1 SN2 E1 E2 reactions, alkene reactions, and reactions of alkynes. So let's go ahead and begin with stereochemistry. What is the relationship between these two compounds? Would you say they're constitutional isomers, enantiomers, diastereomers, meso compounds? What would you say? Now, these two are definitely isomers. Isomers have the same chemical formula, but a completely different structure. Both of these molecules have 5 carbon atoms, 12 hydrogen atoms, and 1 oxygen atom. So they have the same chemical formula, but notice that they're connected differently. Here, the hydroxyl group is on the 2nd carbon. Here, it's on the 3rd carbon. So whenever you have compounds with the same chemical formula but different connectivity, what you have is constitutional isomers. Constitutional isomers have different names. This is called 2-pentanol, and this is called 3-pentanol. Now, what would you say is a relationship between these two compounds? Now, these two compounds are what is known as enantiomers. Enantiomers are a type of stereoisomer. Now remember that constitutional isomers, they have the same chemical formula but different connectivity. Stereoisomers, they also have the same chemical formula, but the atoms are arranged in space differently. Enantiomers, diastereomers, cis trans isomers, all of those are subcategories of stereoisomers. Now, enantiomers, all the chiral centers will have different configuration. A chiral center is basically a carbon atom or an atom that has 4 different groups. So that carbon has 4 different groups here. The carbon highlighted in red. It has a hydroxyl group, a hydrogen, a propyl group, and a methyl group. So that's a chiral center or an asymmetric center. Now notice that the configuration of each chiral center is different. Using the Kahn-Ingold process, we can rank the 4 different groups. The hydroxyl group is going to be number 1. The oxygen has the highest atomic number. The propyl group will carry more weight than the methyl group, so this is going to be group 2, 3, and hydrogen is typically group number 4. So if we count it from 1, 2 to 3, notice that we're going in the counterclockwise direction, and that will give us the S configuration. Now for the other one, hydrogen is in the front. So this is going to be 1, 2, 3. This would look like it's S, but because H is in the front, we need to reverse it, so we get the R configuration. When all of the chiral centers have different configurations, and if the molecule doesn't have symmetry, then the pair of compounds will be enantiomers. Enantiomers are mirror images of each other. They're non-superimposable. They have different physical properties. So they have different melting points, different boiling points, different densities, different solubilities. But enantiomers have the same optical properties. They're optically active, and the way they rotate plane polarized light is opposite to one another. So for instance, the R isomer of a completely different compound might have an observed rotation of positive 18 degrees. The S isomer will rotate plane polarized light in the other direction, so this will be negative 18 degrees. So this would be in the counterclockwise direction, this will be in the clockwise direction. The formula for specific rotation is this. It's equal to the observed rotation divided by the path length, which is in decimeters, times the concentration, which is in grams per milliliter. By the way, for those of you who want more practice problems on a specific rotation, feel free to check out the links in the description section below, because I'm going to have a video that covers this. Now, something that you may be tested on is something called enantiomeric excess. So let's say if we have a solution that is 80% S and 20% R. The enantiomeric excess will be 60% S, because we have more S than R by 60%. So if we have a solution that's 60% in excess of S, what that means is that 40% is a racemic mixture. The other 60% is the excess in the S isomer. So what this means is that if you take 1/2 times 40 plus 60, you're going to get the amount of S that's in the solution. This 40% is a racemic mixture of both R and S. If you want to calculate the amount that's just R, it's just 1/2 of 40. And there's none in excess of R, so this will be just 20% R. But if you look at that video in the description section, it's going to have practice problems that will show you how to calculate enantiomeric excess and things like that. Now, what is the relationship between these two compounds? So let's say we have a Fischer projection of 2-bromo, 3-chloro, pentane. And I'm going to draw another one. So what's the relationship between those two compounds? Are they the same? Are they identical? Are they completely different compounds? Constitutional isomers, enantiomers, diastereomers, meso compounds? What would you say? First, let's determine the configuration at each chiral center. Notice that we have 2 chiral centers. The number of stereoisomers that are possible here is 2 to the n. So because we have 2 chiral centers, we can have potentially 4 stereoisomers. The 4 possible stereoisomers that we can have is RR, RS, SR, and SS. So that's a common test question, how to find the number of stereoisomers given the number of chiral centers. But now to determine the configuration at the chiral center for a Fischer projection, whenever you see hydrogen on the left or on the right, treat it as if it's in the front. So you're going to reverse it. So focusing on this chiral center, the bromine atom has the highest atomic number. It's going to be number 1. H is going to be number 4. Comparing methyl with this entire group, we have carbon, carbon, hydrogen, chlorine. Chlorine's going to win. So the bottom group is 2, methyl is 3. So going from 1 to 2 to 3, it appears to be going in a clockwise direction, which is R, but when we reverse it, we're going to get S. So we have the S configuration here. Now for the chiral center at the bottom, for the chlorine atom, that's going to be group number 1. Ethyl, compared to this group, this is going to be group number 3. The top group is number 2, the bottom group is 3, H is 4. So going from 1 to 2 to 3, this looks like it's going in the counterclockwise direction, which is S, but H is in the front. We're going to reverse it and get R. So this is S, this is R. Now notice here the bromine is on the right side, here it's on the left, so this is going to be R, and this is going to change from R to S. So notice that the configuration at each chiral center is different, and we don't have any symmetry in this molecule. So what we have is a pair of enantiomers. Now, what's the relationship between these two compounds? What would you say? Are they the same, different? Do we have constitutional isomers, diastereomers, meso compounds? What's the relationship between those two compounds? Well, let's find the configuration. Even though we don't need to, but let's go ahead and do that. So right now, we know that H is in the back. So the OH will be number 1. If we compare these two carbons, this one's going to win because it has the hydroxyl group. So this will be number 2, 3, H is 4. So count it from 1 to 2 to 3. It's going clockwise, so that's R. H is in the back, so we don't need to change it. So we have the R configuration. Now for the other chiral center, this is number 1, number 2, 3, H is 4. So this is counterclockwise, that's S. Now here the configurations stay the same. So this is going to be R. Here the hydroxyl group is in the back instead of being in the front. So this is going to change from S to R. So notice that only one chiral center changed. Whenever you have two compounds where some of the chiral centers change but not all of them, what you have is diastereomers. So diastereomers are a type of stereoisomer. We have the same chemical formula, but the atoms, the way they're arranged in space, is different. Now, this particular diastereomer, notice that it has two groups in the same side. This is the cis isomer. Here, these two groups are on opposite sides, so this is the trans isomer. So whenever you have cis and trans isomers, you have diastereomers. But not all diastereomers are cis trans isomers. So make sure you know the difference. So cis-trans geometric isomers are a form of diastereomers. Diastereomers have completely different physical and optical properties. Enantiomers have different physical properties but the same optical properties. That's another key point that you want to keep in mind for your tests. So diastereomers, they have different melting points, different boiling points, different densities, different solubilities, and the way they rotate plane polarized light is different. Now consider these two compounds. What's the relationship between these two compounds? And what can you conclude about their boiling points? Which of these two molecules will have the higher boiling point? Now this is the cis isomer, also known as the Z isomer. The chlorine atoms are on the same side, and they're the high priority groups, so that gives you the Z isomer. This is the trans isomer, also known as the E isomer. So we have cis and trans geometric isomers, also known as diastereomers. Now, which one will have a higher boiling point? If we were to draw the dipole moment, Chlorine is more electronegative than carbon, so it's going to point towards chlorine. Now notice that these two dipole moments, they cancel each other out because they're in opposite directions. These two dipole moments, they're additive. So we have a net dipole moment going in a positive y direction. So because the cis isomer has a higher dipole moment than this particular trans isomer, the cis isomer is going to have a higher boiling point because it's going to have more intermolecular forces operating on it. The boiling point for cis 1,2-dichloroethene is around 60 degrees Celsius. The boiling point for trans 1,2-dichloroethene is around 48 degrees Celsius. And the reason is because this has a higher dipole moment, making it more polar, and as a result, there's more intermolecular forces that must be overcome. So that's why a higher temperature is required to boil it from a liquid phase to a gas phase. Now let's go back to these questions. So what is the relationship between these two compounds? Are they identical? Are they different compounds? Do we have meso compounds, enantiomers, diastereomers, constitutional isomers? What's the relationship here? So notice that the configuration stayed the same at the first chiral center, but it changed at the second chiral center. So if we assume, not to say that it is, but if we assume this is R, this will remain R. If we assume this is R, this will switch to S. This is just a fast way of getting the answer. So some, but not all of the chiral centers change. So what we have here are a pair of diastereomers. Now what about these two examples? What's the relationship between these two compounds? Feel free to pause the video and work on that example. I'm going to write up another one. So if we assume these two are R, notice that they didn't change. So what we have here are identical compounds. They're connected the same, they have the same number of atoms, and the configuration is the same. Now what about for the next pair? Let's assume these are R. This would switch to S, and this would switch to S as well. So the configuration of all chiral centers changed. What do we have here? When the configuration of all chiral centers change, you have two options. Either it's enantiomers or meso. Now, to distinguish them, look for a plane of symmetry. Here, these are different, so there's no plane of symmetry, so it's going to be enantiomers. Enantiomers are optically active. They do not have a plane of symmetry. Meso compounds, they're optically inactive. They do have a plane of symmetry. Go ahead and try these two examples. And while you're working on that one, I'm going to write up another one. Okay, let's start with the first pair on top. What's the relationship between these two compounds? So let's assume that the configuration is R. Both configurations were inverted, so we're comparing RR with SS. So all the chiral centers, they change their configuration. So we either have enantiomers or meso compounds. But notice that we do have a plane of symmetry. The left side is the same as the right side. So because we have a plane of symmetry and all the chiral centers have been inverted, what we have here are meso compounds. Meso compounds are identical compounds. So they have the same exact properties. Now for the next one, let's assume this is R and let's say this is S. This would switch to S, this would switch to R. So R was changed to S was changed to R. All the configurations changed. And notice that we do not have a plane of symmetry. The left side is not the same as the right side. One bromine is in the front on the wedge, the other one is in the back going into the page on the dash. So this is coming out of the page, that's going into the page. So because we don't have a plane of symmetry, what we do have is a pair of enantiomers. Now remember, enantiomers are optically active. And the reason why they're optically active is that they don't have a plane of symmetry, which means they can rotate plane polarized light. Meso compounds are optically inactive because they have a plane of symmetry. Therefore, they won't have any optical properties. They're not going to rotate plane polarized light the way that enantiomers do. Now here's another question for you. So consider this molecule. How many stereoisomers do we have in this molecule? What's the number of stereoisomers in this molecule? Is it 2, 4, 8, 16, 32? What would you say? What we need to do is count the number of chiral centers or stereocenters in this molecule. So we're looking for the carbon atoms that have 4 different groups. This carbon atom doesn't have 4 different groups. These 3 methyl groups are the same. That carbon atom, it's tertiary. Tertiary or quaternary carbon atoms, those are the ones that typically have 4 different groups, but not always. So this is one group, a tert-butyl group. This carbon has a hydrogen, that's the second group, and this side is different from this side. The right side doesn't have a bromine atom, but the left side does. So that will be a chiral center. It has 4 different groups. This carbon is a chiral center. It has a bromine atom, a hydrogen atom that we don't see, and the left side is different than the right side. The first carbon on the right is tertiary. The first carbon on the left is secondary. So those carbons are different, which makes this a chiral center. Here we have another chiral center. This is group number 1. That is the left side. The right side is group number 2. This is number 3. And H makes 4. So that's a chiral center. This carbon is a chiral center too. We have a hydroxyl group, a hydrogen, this group, and that group. Now, this is not a chiral center because it has 2 identical methyl groups. And this secondary carbon is not a chiral center because it has 2 hydrogen atoms. So we only have a total of 4 stereocenters, or 4 chiral centers. And we know that the number of stereoisomers is equal to 2 raised to the n, where n is the number of chiral centers. So it's 2 to the 4, which is 16. So we have a total of 16 potential stereoisomers for this compound. Now, what about this example? So in this example, we're going to have 3 chiral centers as opposed to 2. What is the relationship between these 2 compounds? I'm going to have 3 halogens this time. So feel free to pause the video and try this problem. By the way, if you like this video, feel free to share it with your classmates. If you know anyone else who is taking exam 2 the same time as you, feel free to share this video with them. Maybe this will help them to improve their next exam score. So going back to this question, what do we have here? Is it meso compounds and enantiomers? Are they identical? Do we have constitutional isomers, diastereomers? What's the relationship between these 2 Fisher projections? So let's assume that this is R. This chiral center didn't change. Let's assume all of them are R. Now notice we have an issue. On carbon 3 we have a chlorine, but on carbon 3 here we have a fluorine. Automatically when we see that, we know that the connection is different. Because they're connected differently, we automatically have constitutional isomers. We don't really have to look at the chiral centers anymore. We don't have to look at their configuration. Now let's say if you're given a perspective formula, something that looks like this. What is the configuration at the chiral center? So does the carbon atom, does it have an R configuration or an S configuration? By the way, for those of you who want more example problems on stereochemistry, in addition to specific rotation, feel free to check out the links in the description section below. I'm going to post some videos on stereochemistry and specific rotation with additional example problems. Now this one is a little bit harder because group number 4 is not in the back, nor is it in the front. Bromine is group number 1, the hydroxyl group is number 2, methyl is number 3, hydrogen is number 4. In a situation like this, we can't just go ahead and count it from 1, 2 to 3. We need to use a certain technique. What I'm going to do is I'm going to put the group that's in the back, in a circle, and that's group number 3. Number 1 is on top. To the right of 1 we have 2, and to the left of 1 we have number 4. What I need to do is I need to rotate this molecule and flip it so I can put number 4 in the back or in the circle. So I'm going to rotate this molecule in the clockwise direction. So 3 is going to remain in the circle. The circle represents what's in the back. Number 4 is going to be on top. 1 is to the right. 2 is going to be to the left. I want 4 to be in this position. Now I'm going to flip the molecule. When I flip it, 4 is going to kick out 3. 1 and 2 is going to flip upward. So group number 4 is in a circle, which means it's in the back. Number 3 is now below it. 2 and 1 has been flipped up. So now we can count it from 1, 2 to 3, and this is going in the counterclockwise direction. So that gives us the S configuration. So that's the configuration at the chiral center. It's going to be S. And my video on stereochemistry has more example problems using this technique. Let's try another problem similar to this. So let's say we have an ethyl group in the front. Let's say this is hydrogen. We have a methyl group and a chlorine group. Go ahead and determine the absolute configuration of the chiral center. So the chlorine group is going to be number 1, ethyl is number 2, methyl is number 3, hydrogen is number 4. So we're going to put 2 in a circle, but this time what's in the circle doesn't represent what's in the back. It represents what's in the front, because the ethyl group is coming out of the page. It's on the wedge, it's not on the dash. Group number 1 is on top. To the right of 1 we have number 4. To the left from 1 we have number 3. So I need 4 to be in this position, so I'm going to rotate it in the counterclockwise direction. Two is still in the front. 1 is now in this position, 3 is to the right. So now I'm going to flip the molecule. 4 is going to kick out 2, and 1 and 3 will flip in the upward direction. So now group number 4 is in a circle, which means it's in the front. 1 and 3 are now at the top, 2 is at the bottom. So we're going to count it from 1, 2 to 3. This is going in a counterclockwise direction, that's S, but group number 4 is in the front, so we're going to reverse it, and we're going to get R. So this carbon has the R configuration. By the way, I want to ask you, the viewer, a question. Out of the 4 chapters in this exam review, which chapter do you find the hardest to understand? Is it stereochemistry? Is it SN1 SN2 E1 E2 reactions? Is it alkene reactions or reactions of alkynes? I'm curious to know what your answer is. Feel free to post your comments under the video below. Now let's get back to the review. So the next thing we're going to talk about has to do with SN1 SN2 E1 E2 reactions. So let's start with the SN2 reaction. The SN2 reaction is S stands for substitution, N is nucleophilic, 2 second order. So it's a second order nucleophilic substitution reaction. Here's a good example. Consider the reaction between hydroxide and methyl bromide. Bromine is more electronegative than carbon, so it has a partial negative charge. Carbon is more electropositive than bromine, so it's going to be partially positive. Therefore, the hydroxide is electrostatically attracted to the partially positive carbon atom. So this is going to behave as a nucleophile. It's going to attack the carbon and expel the leaving group. When hydroxide abstracts a proton, it's behaving as a base, but when it attacks a carbon atom, it behaves as a nucleophile. So the SN2 reaction, it's a concerted reaction mechanism. The bond between oxygen and carbon, it's forming at the same time this bond is breaking. So that's a concerted reaction mechanism. It happens all in one step. So the leaving group is going to leave, and we are going to get methanol and bromide. So that's the mechanism for the SN2 reaction. Because it occurs in a single step, the energy diagram is only going to have one transition state. This is the transition state, this is the energy of the reactants, this is the products. On the y-axis we have potential energy. On the x-axis that's the reaction coordinate. The forward activation energy is the difference between the energy of the transition state and the energy of the reactants. The reverse activation energy is the difference between the energy of the products and the energy of the transition state. Now here is the rate law expression for the SN2 reaction. The rate of the reaction depends on the concentration of the substrate. The substrate is the alkyl halide, and it also depends on the concentration of the nucleophile, which in this case it's a hydroxide. So if you add the exponents, it's second order overall. So that's the SN2 reaction. It's a second order nucleophilic substitution reaction. So what this means is if we double the concentration of the substrate, the rate is going to double. If we triple the concentration of the nucleophile, 3 to the first is 3, the rate is going to triple. If we were to double the concentration of the substrate and triple the concentration of the nucleophile, the rate will increase by a factor of 6. 2 times 3 is 6. So the rate depends on both the concentration of the substrate and the nucleophile. Now the SN2 reaction, it works very well with polar aprotic solvents. Polar aprotic solvents are those that don't have hydrogen bonds like OH or NH groups. So a good example of a polar aprotic solvent is acetone. It doesn't have any OH groups. Another one you'll see is DMF, and then there's DMSO, dimethyl sulfoxide, which looks like this. Crown ethers. These are all good for SN2 reactions. This is the 12 crown 4 ether. It has 12 atoms, 4 of which are oxygen atoms, and this is good for the lithium ion. The 15 crown 5 ether is good for solvating the sodium ion. The 18 crown 6 ether is good for solvating the potassium ions. So one of the advantages of using crown ethers is, let's say if we want to use sodium hydroxide as our nucleophile, the 15 crown 5 ether will solvate the sodium cation. As a result, this allows the hydroxide to be free to react with the substrate. So by solvating the cation, it makes the nucleophile more nucleophilic, which enhances the SN2 reaction. Now let's talk about substrate reactivity. The SN2 reaction, it works better with methyl halides. Methyl halides are more reactive than primary alkyl halides. Primary alkyl halides are more reactive than secondary alkyl halides. And the SN2 reaction doesn't work when dealing with tertiary alkyl halides. Now sometimes you may be given a reaction and you have to predict the major product, and you need to know what mechanism the reaction will proceed by. So there's a video that I have on YouTube entitled SN1 SN2 E1 E2 reactions, and it has a table where if you know the substrate, the solvent, and the nucleophile that you're using, or the base, you could determine if it's SN1, SN2, E1, or E2. I'm going to post a link to that video in the description section below, so you could take a look at that when you get a chance. But know that for the SN2 reaction, methyl halides are more reactive than primary halides. Tertiary halides are the least reactive. For the SN1 reaction, the situation is reverse. Tertiary alkyl halides react faster in an SN1 reaction than secondary alkyl halides, and so forth. The reason for this has to do with carbocation stability. A tertiary carbocation is more stable than a secondary carbocation. And that's why tertiary alkyl halides work better for SN1 reactions than secondary alkyl halides. It's because tertiary carbocation is more stable. For the SN2 reaction, you need to look at steric factors. Tertiary alkyl halides are not good for the SN2 reaction because it's very hard for the nucleophile to access that carbon. It's sterically hindered by the methyl groups. So if we were to add hydroxide and try to use it as a nucleophile, it's going to be very difficult for it to approach this carbon from the back because it has 3 bulky methyl groups in its way. So that's why SN2 reactions work better with methyl and primary halides, is because the carbon that bears the bromine is not sterically hindered. It's accessible to attack by a nucleophile. But SN1 reactions, they work better with tertiary alkyl halides because of the stability of the carbocation. So let's talk about the SN1 reaction mechanism. So what we're going to do is we're going to react a tertiary alkyl halide with, let's use water. In the first step, the leaving group is going to leave. By the way, water is a weak nucleophile. So it's going to wait until the leaving group leaves. Then water is going to add to the carbocation. We're going to get an oxonium ion. And then another water molecule is going to act as a base, removing the hydrogen, giving us a tertiary alcohol. So here, water is acting as a nucleophile when it reacts with a carbocation, but here it reacts as a base when it abstracts as a proton. So that's the difference between a nucleophile and a base. A nucleophile, within the context of organic chemistry, will typically attack a carbon atom. A base will abstract a proton. So this particular S1 reaction is known as a solvolysis reaction. Think of the word solvo, solvent, and lysis. So we're using the solvent to basically split apart the carbon-bromine bond. Lysis means to split apart. In a solvolysis reaction, which is typically SN1 reaction, if you see it, it's always an SN1 reaction for the most part. But that's when the solvent reacts as a nucleophile. If we were to draw the energy diagram for this particular SN1 reaction, notice that we have 3 steps. This will be the first step, the second step, and then the third step. If the energy of the products is less than the energy of the reactants, what we have is an exothermic reaction. If the energy of the products is higher than the potential energy of the reactants, we would have an endothermic reaction, or an endergonic reaction, if you're looking at it from the delta G perspective. So because we have 3 steps, we're going to have 3 transition states. This carbocation intermediate is the first one, and this oxonium intermediate is the second one. Notice that this intermediate is lower in energy than this one. Intermediate 2 is more stable than intermediate 1. Even though oxygen is more electronegative than carbon, and it doesn't want to have the positive charge, intermediate 2 obeys the octet rule, whereas intermediate 1 does not. We have an empty p orbital. Carbon doesn't have 8 electrons, it has 6 or 3 bonds. So that's why intermediate 2 is slightly more stable than intermediate 1. So it's lower in energy in the energy diagram. Now let's say if we were to have tert-butyl-bromide, and if we were to react it with potassium iodide. So this is a tertiary alkyl halide. It's going to favor an S1 reaction. The first step, the leaving group is going to leave. In the next step, the nucleophile is going to add itself to the carbocation. And we get tert-butyl iodide. Now, this was a 2-step reaction because the nucleophile was negatively charged. When the nucleophile is neutral, you're going to have an extra step, which is going to be a proton transfer step, and that's why that SN1 reaction occurred in 3 steps, whereas this one, it occurred in 2 steps. So for a 2-step SN1 reaction, the energy diagram is going to look like this. We're going to have 2 transition states and only 1 intermediate. Now let's talk about the rate law expression for an SN1 reaction. The rate only depends on the concentration of the substrate. It doesn't depend on the concentration of the nucleophile. Keyword SN1, first order nucleophilic substitution. It's first order overall. If you add the exponents, you just get 1. Now let's talk about why it depends only on the concentration of the substrate. The first step is the slow step. That's the rate determinant step. Notice that the nucleophile does not participate in the first step. It participates in the second step, which is the fast step. And the rate doesn't depend on the fast step. That's why the nucleophile is not included in the rate law expression. So what does this mean? If we were to double the concentration of the substrate, the rate for the SN1 reaction would double. If we were to double the concentration of the nucleophile, the rate for an SN1 reaction would not be affected because the concentration of the nucleophile is not in the rate law expression. The rate for an SN1 reaction does not depend on the concentration of the nucleophile. So make sure you understand that difference between an SN1 reaction and an SN2 reaction. If you were to double the concentration of the nucleophile in an SN2 reaction, the rate would double. If you double the concentration of the nucleophile in the SN1 reaction, it would have no effect on the rate. Now here's a typical test question for you. Looking at these alkyl halides, which one will react the fastest in an SN1 reaction, and which one will react the fastest in an SN2 reaction? Feel free to pause the video. So what we have here is a secondary alkyl halide. This is tertiary and this is primary. So for a primary alkyl halide, this is going to react the fastest in an SN2 reaction. The one with the tertiary alkyl halide will react the fastest in an SN1 reaction. Now here's another question for you. Consider these 2 alkyl halides. Which one will be better in an SN1 reaction? The one on the left or the one on the right? So which is better for an SN1 reaction? Which one will react faster? Now in both cases we have a secondary alkyl halide. Now this one is adjacent between a primary and a secondary. This one is between a secondary and a tertiary. This one is going to win because of carbocation rearrangements. When the bromine atom leaves, we're just going to get a secondary carbocation, which is 2 carbons away from the tertiary carbon. When the bromine atom leaves here, we're going to get a secondary carbocation that's adjacent to a tertiary carbon. And so we're going to get what is known as a hydride shift, a carbocation rearrangement. The hydride is going to glide towards the carbocation, and when the hydrogen moves here, we're going to have a plus charge on a tertiary carbon because it lost the bond. And tertiary carbocations are more stable than secondary carbocations due to hyperconjugation and the inductive effect. And so this is going to react faster in an S1 reaction because it could form a more stable carbocation intermediate. It's going to be a lot harder for the carbocation to rearrange when it's 2 carbons away from the tertiary carbon as opposed to being 1 carbon away. So this is going to react faster. Alright, here's another question for you. Which one of these alkyl halides will react the fastest in an SN2 reaction where methanol is the solvent? So which one will react the fastest? What would you say? In all cases, we're dealing with a secondary alkyl halide. The only difference is the leaving group. So what we're looking at is leaving group stability. Which leaving group is the best in a protic environment? Iodide is a better leaving group than bromide, which is better than chloride, which is better than fluoride. And the reason for this has to do with atomic size. So here's the halogens on a periodic table. Atomic size increases as you go down. Iodide is simply a much bigger ion than fluoride, for instance. Fluoride is a smaller ion, and so that negative charge is concentrated in a smaller region, making it less stable, more reactive. Whereas in the case of iodide, the negative charge is dispersed over a larger area, so that negative charge is less concentrated, making it less reactive, more stable. Iodide is a weaker base than fluoride. Fluoride is a stronger base than iodide. The weaker base is going to be the better leaving group. So because we have a better leaving group, this is going to be the answer. So this is going to be the alkyl halide that react the fastest, 2-iodopentane. It's going to react the fastest in the SN2 reaction because it has the best or the most stable leaving group. So it's going to be very easy to kick off the iodine atom. Now here's a question for you. Which one is a better leaving group? The acetate ion or ethoxide? What would you say? Which is the better LG? Now, by the way, for those of you who want more example problems on SN1, SN2, E1, E2 reactions, I do have a practice test on this chapter, and it's about 77 questions. It's very long, very comprehensive. And if you go to YouTube and type in the search bar SN1, SN2, E1, E2 practice tests, you'll see a video that has the first 15 questions free. The full version has all 77 questions, and I'm going to post that in the description section below. But going back to this question, which one is the better leaving group? Acetate or ethoxide? So let's look at the conjugate acid. The conjugate acid for acetate is acetic acid. For ethoxide, it's ethanol. Now the pKa for ethanol is 15.9. For acetate, or acetic acid rather, it's 4.75. Now we know that the lower the pKa value, the stronger the acid that we have. So this is the stronger acid, this is the weaker acid. The stronger the acid, the weaker the conjugate base. And the better leaving group is going to be the weaker base. So this one is the better leaving group. And it has to do with the stability of the negative charge. This negative charge is stabilized by resonance. That negative charge can delocalize into the carbonyl functional group. And so it's shared among 2 oxygen atoms. Here, the negative charge is localized on 1 oxygen atom. As a result, this is not a good leaving group. this is the better leaving group. So this is going to be the answer. There's a video that I have entitled Stability of Negative Charges, and it relates to, which one's going to be the better leaving group. So the one with the most stable negative charge will be the better leaving group. If you go to YouTube and type in Stability of Negative Charges Organic Chemistry Tutor, that video is going to show up. And it covers 7 factors, if I remember correctly. That is atomic size, electronegativity, hybridization, resonance or electron delocalization, which we just covered. And there were some other factors. Aromatics, and there was something else. I forgot what it was, but solvent effects, that was another one. And once you watch that video, it's not too long, but it'll cover 6 or 7 factors that affect the stability of negative charges. And using those factors, you can identify which one will be the better leaving group. Now let's move on. Let's say we have butyl-bromide and we're reacting it with potassium fluoride using a 15 crown 5 ether. And let's compare that with, let's say, potassium chloride. Actually, let's use potassium iodide. And we'll use the same 15 crown 5 ether, which will solvate the potassium iodide. And we'll dissolve both solutions in benzene. Now, potassium fluoride is not soluble in benzene, but the crown ether actually increases the solubility of potassium fluoride in benzene. So you could think of this as a phase transfer catalyst. But for those of you who want to get deeper into that, I do have a video on crown ethers. It'll talk more about that topic. But right now, the only difference that we have here is the choice of the nucleophile. And looking at these two reactions, which one would you say is more reactive in an SN2 reaction? This is going to be SN2 because both alkyl halides are primary, and we have a polar aprotic solvent which favors an SN2 reaction. But which of these two reactions will react faster in an SN2 reaction? Since the only difference is the nucleophile, the question is really, which nucleophile is better? Which one is going to be more reactive? Is it iodide or fluoride? The answer has to do with the choice of the solvent. In a protic solvent, iodide is going to be the better nucleophile. The reason for that is the protic solvent, like water, it will solvate the fluoride ion better than iodide. Fluoride is a stronger base, so it's going to have more interaction with the hydrogen bonds of water. So because this will be solvated by the protic solvent, it's going to be less available to react with the alkyl halide as a nucleophile. But in an aprotic environment where the solvent solvates the cation, fluoride is free to react. And because fluoride is a stronger base than iodide, it's going to be a better nucleophile in an aprotic environment. So make sure you know this difference. Iodide is a better nucleophile than fluoride in a protic solvent, and fluoride is a better nucleophile in an aprotic solvent. So because we have an aprotic solvent, the crown ether, this one is going to be the faster reaction. Fluoride is going to be a better nucleophile than iodide in an SN2 reaction in an aprotic environment. So you need to know the difference between a protic solvent and an aprotic solvent. So to review, let's go over the difference. So protic solvents are those that have hydrogen bonds like water, methanol, also known as MEOH, Me for methanol. Ethanol is a protic solvent. You can write that as ETOH. ET stands for ethanol, or rather ethyl. Acetic acid, that's a protic solvent. Ammonia, it has hydrogen bonds, so that will be in the protic solvent category. We've covered most of the aprotic solvents like dimethyl sulfoxide, DMF. HMPA is another one if you see it. Crown ethers. THF, that's another aprotic solvent. It looks like this. And one of the most common ones you'll encounter is acetone, which is a ketone. So remember, aprotic solvents favor SN2 reactions, and protic solvents are good for SN1 reactions. An SN2 reaction can occur, it could occur in a protic solvent. It's just SN2 reactions work better in an aprotic environment. So keep that in mind. Now going back to nucleophiles. Some good nucleophiles that you need to be aware of are iodide, that's a good nucleophile in a protic environment. If you see sulfur with a negative charge, that's a good nucleophile. If you see cyanide, these will enhance the reactivity of an SN2 reaction. There are some other good nucleophiles as well, but those three are the most common good nucleophiles. When you see them, typically they're usually associated with an SN2 reaction. When you're using a protic solvent like water, methanol, or ethanol, a lot of times these are associated with an SN1 reaction, and SN1 reactions tend to occur with E1 reactions. When water is behaving as a nucleophile, it's a weak nucleophile. That's usually going to be an S1 reaction. When it's behaving as a weak base, you're going to get an E1 reaction. E1 reactions work well with weak bases. E2 reactions work well with strong bases. Now here's a question for you. Which of these two reactions will work faster? And would you say this would be an S1 reaction or an E1 reaction? In the first example, we're going to have 80% water, 20% methanol. So we have a solvent mixture. In the second example, we're going to have 50% water and 50% methanol. So in both cases, what we have is a secondary alkyl halide. This carbon is attached to two other carbon atoms. Now, when dealing with a secondary alkyl halide, it could be an SN2 reaction, it could be an S1 reaction. So you need to look at the solvent and the nucleophile. In both cases, we have protic solvents, so that's going to favor the SN1 mechanism over the SN2 mechanism. We don't have a good nucleophile, we have a weak nucleophile and a weak base. So because they're weak, that's going to favor an S1 mechanism. So which reaction will work faster in an S1 environment? Is it the first one or in the second one? Now in both cases, we're dealing with protic solvents. Now it's important to understand that S1 reactions, they work well with polar protic solvents. An SN2 reaction works well with polar aprotic solvents. Notice the commonality here. Keyword is the first one in the phrase, polar. The SN1 and SN2 reactions, they're not very good in nonpolar solvents. They're good in polar solvents. So the real question for this one, to determine which one's going to react faster, is which solvent mixture is more polar? So which solvent is more polar, water or methanol? If we were to draw water, water has two OH bonds, methanol has one OH bond. The methyl group is the nonpolar part of methanol. The CH bond is nonpolar. Water doesn't have any nonpolar region in it, so water is going to be more polar than methanol. Even though methanol is polar, it's less polar than water. So because this mixture has a higher concentration of water, and water is more polar than methanol, this is going to react faster in an S1 reaction. It's because the solvent mixture is more polar. This one is going to be slower in an S1 reaction. Now let's talk about the stereochemistry of the SN1 and SN2 reaction. So here we have 2-bromo-butane, and let's react it with potassium iodide in acetone. What's going to be the predominant mechanism here? So we have a secondary alkyl halide, we have a good nucleophile, iodide, and we have a polar aprotic solvent, acetone. This is going to favor an SN2 reaction. The nucleophile is going to attack from the back and is going to kick out the leaving group. The SN2 reaction occurs with inversion of configuration. So if we were to determine the configuration at the chiral center, this would be group number 1, 2, 3. H is 4, counted from 1, 2 to 3. We're going clockwise, so that's the R configuration. Now the configuration is going to be S because iodine is in the back, which means hydrogen is in the front. So notice that we have inversion of stereochemistry. So an SN2 reaction will give us 100% inversion. The SN1 reaction is different. So let's react this with potassium iodide in water, and we're going to use iodide as a nucleophile. Now before iodine reacts, the leaving group is going to leave. And then the nucleophile can attack the carbocation from 2 directions. It could attack it from the back, that is away from the bromine atom, or it could attack it from the front, which is closer to where the bromine was. There's something known as the intimate ion pair. When bromine leaves, it may not be too far apart from the carbocation. So rather than being completely dissociated into the solvent, sometimes it could be relatively close, unless you give it more time where the solvent will dissociate it away from the carbocation. Now, if iodide attacks from the back, we're going to get the inverted product, which looks like this. If it attacks from the front, we're going to get the retention product. So we're going to retain the stereochemistry at the chiral center. So the S1 reaction, it gives us a racemic mixture. We get both the R and the S isomer. The propyl group is number 1. Actually, we don't need to count that. We just know one of them is going to be R, one of them is going to be S. You can figure it out if you want to. So make sure you understand that the SN2 reaction, it gives us 100% the inverted product, but the S1 reaction gives us a racemic mixture. We get both inversion and retention. Now, which one will be in greater yield? The inverted product or the retention product? What would you say? Notice that when iodide attacks from the back, there's no interference with the bromide ion. But when it attacks from the front, there's interference with the bromide ion. Iodide has a negative charge, bromide has a negative charge. So as it approaches from the front, if bromide is still hanging around that carbocation, it's going to be repelled as it approaches from the front. It's repelled by the negatively charged bromide ion. As a result, we get an unequal racemic mixture. So we may get 60% inversion, 40% retention, sometimes it could be 30-70, but for the S1 reaction, we get slightly more of the inverted product than the retention product due to this intimate ion pair. Keyword intimate, that means they're close to each other, and we have a pair of ions. So the intimate ion pair reduces the yield of the retention product. So that's what you need to know regarding the stereochemistry for the SN1 and SN2 reactions. Now, if you like this video so far, and if you find it to be helpful, feel free to share it with other students or other classmates who are studying for this exam. Feel free to post it on Facebook, Pinterest, Twitter, TikTok, Instagram, Reddit, or whichever other social media platform that you're currently using. Because I know there's other students who struggle with this concept and they could really benefit from this video. So feel free to share it with whoever may need the help as well. Also, one thing I like to ask is, after you take your second exam, after watching this video, let me know what grade you got on your second exam. I'm curious to see how this video has helped you. So feel free to post your grades, if you want to, in the comment section below after taking your second exam. Now, one more thing I want to mention is that for those of you who want access to the full version of this video, feel free to check out the links in the description section below. I'm going to post it there as well, in addition to the other links that I've mentioned earlier in this video. Now, let's move on to E1 and E2 reactions.